Welcome to the first talk of session 10 of the DSFP. So for those of you that are new to the program, at the beginning of every session, I give a brief overview talk on day one. Okay, so the sort of goal today is that I am hoping to highlight some of the questions that are going to come up throughout the course of this week. I'm not going to answer all of those questions, okay? So I'm going to try to say some provocative things that get the gears turning and get us ready to approach some of the more complex problems that we'll face throughout the course of this week. The title of this first talk is Understanding Data, with the subtitle, or Lies I've Been Told About Statistics. And in particular, I want to talk about the idea of lies, and some of you know I'm sometimes a bit brash or bombastic, but it is actually well known that the first thing that someone learns is actually super hard to unlearn, even if said thing is incorrect. And so we'll talk about some things that people say regarding statistics and model fitting and address whether or not those statements are in fact true. Okay. You can follow along if you do a git pull. The information to get on the Wi-Fi is on the two side screens here. You will not actually be working on any problems immediately, so if you want to just follow on the screen, that works as well. Okay. Okay, so according to the DSFP curriculum, this entire week is going to be devoted to statistics, which is somewhat insane because statistics is, like astronomy or astrophysics, a whole field unto itself. Okay? So that is way too much to tackle in a single week. I think a more apt description for this week's theme is models. Right? This week we'll be talking a lot about models, which I contend is a very good thing because everything in astronomy is a model. Broadly speaking, we aim to build models for two purposes: forecasting and inference. Forecasting is about predicting the outcome of some future, as of yet unobserved event. Okay? So this can be extremely useful. Say, for instance, you can measure the velocity dispersion of some galaxy, and you want to know the mass of the black hole at the center of that galaxy. Right? This is a method of forecasting. As a brief aside, we will not be talking about machine learning this week, but machine learning is primarily concerned with forecasting. Okay? All right. Inference, on the other hand, is about understanding the fundamental relationship between parameters. Okay? So you can use inference for forecasting, right? But the other way around is not always true. Inference is actually necessary for understanding physics. So the following statement can be very useful. If I have 10 measurements of a force applied to some ball, I predict that any newly applied force, F nu, will produce an acceleration F nu divided by m ball, the mass of the ball. Okay? But it is far, far, far more useful to say that F equals ma for any object with mass m. Right? So this is the difference between forecasting and inference. All right. But before we jump in and start talking about models, right, we need to back up, we need to zoom out a bit, because models require data. Okay? At the core of everything that we will do here in the DSFP is data. This is a program on data science. Right? Right, as astronomers, astrophysicists, we have a vast array of telescopes at our disposal. You can combine the information from those various telescopes, both here on Earth and in outer space, in order to collect a whole host of data that allows us to unravel the mysteries of the universe. Right? So this naturally leads to a question: what is data? So we're going to pause now, and I want you to chat with the person sitting next to you. And every other row here is 7 people, so you're going to have to form at least one group of 3. Okay? What is data? All right, let's take a few more seconds to wrap up the discussions. All right, let's wrap up. Okay, and a reminder that you have microphones at your seat. Okay, but who would like to share some of what they talked about with us? If no one volunteers, I'll just randomly turn on your microphones. I do not have that power. Yes, Lucia. Okay.
It's green now.
Yes.
I mean, there's categorical and then there's, numerical data. So you could get states or something like that. You could get like what classes the students have taken, but you could also get age or, longitude, latitude, those sort of things. So data is really something that's been collected that you think you might be able to perform some sort of analysis on that might not yield anything, but you don't know until you analyze it.
Okay, so data is something that has been collected, and you might be able to perform analysis on it, or maybe not. Yes. Any other ideas? Thank you, Lucia. Yeah, Devonta, you have to Mike. Thank you.
We're saying that data is information that is logged. So there's all types of different information.
Yeah, so data information that is logged. Yeah. Any other ideas? Yeah.
So we were talking about how it depends on how you infer or measure the data. So there has to be an error associated with it. And even though it seems like data is sort of a fact, but it should have some ambiguity to it too.
Okay, so data may have some ambiguity. It depends on exactly how it's being measured. Yeah? Okay, great. So yeah, we've heard several different things, all of which I think are great definitions of data. But I want to emphasize, and I really want you to be thinking about this over the course of this week, the following idea, and that is that data are constants. Okay? And this may sound very weird at first, right? But I think we will get there. Okay, but Adam, hold on a second. Hold on, right? So I have some data reduction pipeline, and that pipeline makes data. And sometimes the pipeline doesn't work well, so I can make that pipeline better. And so then my data change because my pipeline's better. So data have changed. How can data possibly be constant? Right? A fair question, okay? This is subtle, right? But in this case, the data have not, in fact, changed, right? The output from the pipeline, which we often think of as data, is in fact actually a model. Right? Adjustments in the pipeline create changes in the model, right? And any downstream analysis, because the model has changed, right? Those changes are because of change in the model itself. Right, so the big idea, the forward takeaway from everything we've talked about so far is that models vary and data don't. Okay? And this is very important for how we're going to interpret every single problem that we encounter this week. Right? So let's just clearly reiterate this particular point in the sense of thinking about, say, optical data that you might take of a star cluster. Okay? So supposing you want to determine the age of this cluster, the typical way to do that is with the main sequence turnoff. So you look for stars on the main sequence that are moving off of the main sequence. This can tell you, and if you know their mass, you can figure out how old the cluster is based on simple models for how hydrogen burns in the core of stars. Okay. But in order to do this, you need to know the flux of every star in the cluster, which you can then compare to your stellar evolution models. Okay. But those fluxes, right, the fluxes that you might go and get in the LSST database are in fact a model. before LSST can actually put anything in the database telling you how bright some particular star or galaxy is, the following things happen, and this is an incomplete list. Right? So you're going to bias subtract your raw CCD image. That's model number 1. Right? This is simple. Right? It's still a model. You're going to flat field correct the bias subtracted image. That's model number 2. Then you have to identify the location of every single star within this image. That's another model. You're going to align the relative pixel positions with some standard astrometric reference frame. That's Gaia these days. But that's another model. We're already up to 4, and we haven't done anything related to measuring flux yet. Okay. Now we have to determine the relative flux of every single star and galaxy in the image. Right? This is model number 5, although it's probably a few models if we're being really fair. And then finally, we're going to convert those relative fluxes to some absolute measurement so that you can actually place these stars on a color magnitude diagram and determine the turnoff age. That's 6 models, and it's probably an incomplete list. Right? And that's just for flux. We're not even talking about like something really cool, like I've measured the mass of this star. Right? So, the flux of a star, which often we would say, yes, my data is a bunch of fluxes and some shape measurements or whatever, is actually a model. And in fact, a model of several models. Right? And so this brings us back to my earlier claim. Everything in astronomy is models. Models all the way down. Right? And in some sense, I actually hope that this makes you a little bit nervous. Right? So have the uncertainties of every single one of those models been properly estimated? And even if they have they been properly propagated to whatever database it is that you're now using to get the fluxes for these sources? Right? Don't worry about that too much, but it's like something like maybe once every 3 months, like just take a day thinking about that, right? Because it should bother you a little bit, okay? Don't let it make you quit astronomy, though. Okay, so models, right? Everything in astronomy is models. Let's talk about linear models and least squares fitting. All right, so there are several cells in this notebook. They are essentially all already pre-populated, so you're not going to have to do any work. So if you prefer to just watch up on the slides, that is perfectly fine, okay? So I just say execute the cell below in order to populate your namespace with some data that we'll use in the subsequent analysis, okay? There we go. All right, so you now have some data X and Y. As a good data scientist, what is the first thing that you will do with data X and Y? Can you repeat that? Okay, so sorry, the mic didn't turn on. So the suggestion was we have the new data, let's plot it. Okay, please raise your hand if that was your first thought as well. Okay, I will say the vast, vast majority of you. I'm sneaky, all right? And I misled you with this question, right? Anytime you're looking at some new data set, it is vitally important to understand where the data came from and what they represent. Okay. More so than plotting. All right. While the data are constants, they do represent measurements of some kind. All right. And so understanding where they came from is vitally important, particularly if we're going to try to do something like inference or forecasting. Right? We might want to understand, is there some bias in the way that these measurements were collected? Okay, all right, so I'll stop being tricky. In this case, right, the data that you've loaded, X, Y, and uncertainties on the Y observations, is just some toy data set. It's literally something that I've simulated using random number generators. Okay? So there's no units, there are no specific measurements, and there's no bias that you know of. All right. Okay, so the next thing I asked you to do is to just create a scatter plot to show the relationship between X and Y. Okay. So here we just are opening a new figure, and then we say plot X and Y with some symbols. And if I, whoops, let's see here. Nope. There we go. Okay. So here is what the actual data look like in this case. Okay. Oh, whoops. Here, this is what the data look like in this case. So I think there's a very good chance that upon seeing that data, and I'm not assuming that this is the case, but I think there's a very good chance that you probably had some thought along the lines of, that data looks like it is drawn from some sort of linear relationship. There's some correlation between the x and the y values that we have here. Okay. And so, question number 2 to discuss with your partner: is the assumption of linearity valid for the above data? Is it convenient? Right? And let's take a minute to discuss this with our partners. All right, let's take a few more seconds to wrap up. All right, let's wrap up. Okay. All right, so we were discussing, is the assumption of linearity valid? Okay. So if you think this assumption is valid, please raise your hands. Yes, remember, honesty is a principle of the DSFP. Okay. All right. If you think this is a convenient assumption, please raise your hands. Okay. All right, so everyone for convenient, fewer people for valid. So let's discuss that a little bit. Okay. Oh, that is not what I meant to do. This is an entirely different talk. Here we go. All right. All right, so one of the lessons that I hope you take away from this morning is that assumptions are dangerous. Okay. So in general, a linear relation between data can only be assumed if there's some very strong theoretical motivation for such a relationship. Okay. An example of this that I keep coming back to is something like F equals MA. Right? That's a linear relationship where we have good theory leading that principle. Otherwise, the relationship could be just about anything. Right? And inference based on the assumption of linearity may lead to dramatically incorrect conclusions. Right? That being said, for the purpose of forecasting, maybe it's just fine. Right? This is a big difference between forecasting and inference. Right? All right, nevertheless, we are going to assume that these data have been drawn from a linear relationship, all right, because that is a convenient thing to assume, particularly when the data look as they did in the plot that we saw a moment ago. There are a large number of tools that are designed to solve this very problem. So if you want to infer a linear relationship between some data. Okay. And I will note, my apologies, I forgot to push the helper functions that you will need to actually load this data. So feel free to continue looking in your notebook, but you won't be able to make any of those plots until the break once I share those files. That was my mistake. I apologize. Okay. So we'll proceed with convenience, all right? And we'll try to understand the underlying relationship between the x and the y coordinates for this data set, okay? So if you go take some class on statistics or you open some stats textbook, all of these things, when dealing with the problem that we're faced with right now, start with least squares fitting, okay? And I won't get into the full mathematics of this, and there are some very nice mathematical properties of least squares fitting, but in brief, a least squares fit minimizes the sum of the squared value of the residuals. So just compare your model to your actual values y, square that difference, sum all of that up, minimize that. That's a least squares fit. Okay? In the case of simple polynomial models, you can actually get an exact answer using least squares fitting with some relatively straightforward matrix multiplication. Again, we're going to skip the mathematics for now. But these are all really nice properties, which is why least squares is a great place to start for something like fitting a line to two-dimensional data. Okay? Today, instead, what we're going to do is rely on Google, which tells us that the easiest way to quickly perform a linear least squares fit with Python is using the NumPy polyfit function. Okay? And basically, with this, you can just perform a least squares fit to two NumPy arrays. All right, so next problem was to use polyfit to fit a line to the data, and then overplot the best fit line. Okay, all right. So I don't necessarily expect you on the fly, and then let me scroll. Okay. On the fly to have all of what I've plotted here, right? But here you can see the same data we had before. The orange line is the result from the least squares fit. And then it's always useful, either for forecasting or inference, to look at the residuals of any model that you may be fitting for data, which is what's shown in the lower panel here. Okay? And the reason that's useful is that you might see some correlation in your residuals that could give you some sense that there's bias in the model that you're using. Right? Okay. By eye, this doesn't look too terrible, right? Seems relatively reasonable. So there's a very good chance, all right? And again, I don't want to assume anything, that were you actually able to make this plot on your own, which you weren't because I failed, that what you would have done is plotted the x along the abscissa and the y along the ordinate, right? And there's no one to blame for this, but no one told you to plot things that way, right? And in fact, this is something that's sort of been drilled into us for as long as we've been taking classes where we make plots. And in fact, even in matplotlib, if you want to change the label on the abscissa, you have to adjust the x label, right? That's how much all of us think x goes this way, y goes this way, right? It's just drilled into us. But this leads to a really important question, though, right? All we have right now is some data, x and y. What if we flip y and x? Does that change the results of our fit at all? Okay, so if you perform a linear least squares fit to x versus y, all right, and then once again plot the best fit to the model, you will get something that looks slightly different. And so to test whether or not these lines more or less are the same, whether our inference is the same, all right, let's compare the values of y that's predicted by the model at x equal to 50. Okay. All right, so here is a solution, not the only solution. So here at the top of the cell, we have polyfit. We've flipped x and y, so we're doing polyfit of y and x. And then we can evaluate that in order to plot the line. So we have some code here plotting that. And then the residuals, just as we had before. And then we can say, OK, what is the equation for x and y? And at x equals 50, what would we forecast as the value of y based on each of these fits? OK, so here is our fit of x versus y. And that more or less looks very similar to what we had previously. Okay. Although there may be a bit of structure in the residuals. Nevertheless, the scatter's not too bad. There's nothing really very obviously going on. Okay. But what about the forecasting? Okay. So when we fit y versus x, we find that at x equals 50, we would estimate a value of y of 167. But when we flip things around and we estimate the value of y at x equals 50, we instead find that y equals 113. Is 167 and 113 the same number? No. Okay, so what's going on here? This, in fact, is lie number 1, right? So the relationship between x and y is not the same as the relationship between y and x, as far as least squares fitting is concerned. This is kind of bonkers, right? This is kind of like saying f equals ma, but no, a does not equal f over m. feel like you should be more bothered by that statement. That's weird. This is weird. This makes no sense, right? So how can this be? What's going on here? Okay. So there are several assumptions, right? And remember, assumptions can be dangerous, that go into standard least squares fitting. The first one is that there is one dimension along which the data have negligible uncertainties. Right? So we're saying, essentially, typically, if you are fitting y versus x, we're saying that there is no uncertainty on the measurements that have been made for the value of x. So just think about how many scatter plots you've made in your life where there's uncertainties on both axes. Right? Linear least squares doesn't work then. Right? The other major assumption is that along the other dimension, right, all of the uncertainties can be perfectly described by Gaussians of known variance. Okay? So the uncertainty on y is a Gaussian for every single observation, every single data point in your data set. Right? If these two conditions are not satisfied, linear least squares is not an appropriate way to determine the relationship between your data. Right? And I contend that within astronomical data, satisfying both of these conditions is rarely the case. Okay? You can satisfy the first condition, right? We know timing really well. So like suppose you're going to measure the flux of some star as a function of time, right? Every timestamp associated with every measurement there essentially has negligible uncertainty. Right? But to have absolute certainty that your uncertainties are Gaussian with known variance, right? Remember that in astronomy, it's all models. It's models built on models, built on models, built on models. And are you sure that by the time you've gotten to the 8th model, which is your data, okay, that actually your uncertainties are Gaussian at that stage? All right. So that brings me to problem number 3. Lies, damned lies, and statistics. All right. All right. So maybe I was stretching the truth a little bit when I said that we just uncovered lie number 1, right? The relationship between y and x must be the relationship between x and y. It's just that there are assumptions that go into linear least squares if you want to try to infer said relationship. But there are many, many, many misconceptions that are associated with model fitting, and in particular, things like fitting polynomials to data, which is, as we talked about, kind of like the gateway to understanding how you would fit models to data. Within the context of least squares, which tends to be the first thing we learn, which means it's something that's very hard to unlearn. And so I want to try to address some of those things now. All right, so we're going to go through some lies, and I'm going to ask you to raise your hand if you've heard something similar at any point. Okay, so lie number 2. If you have some two-dimensional data set with one dependent variable, so y depends on x, so this means that we actually have a pretty good handle that perhaps we do have something where linear least squares would work, and you have n observations, so there's n points in your data set. A polynomial of the nth degree can perfectly fit the data. So if you've heard this or something very similar to this, please raise your hand. Okay. We have maybe 50%-ish, maybe a little bit more. Okay. All right, so what if our data set looks like the following? And we have to do this. All right. Can you fit this with a polynomial? I can give you an infinite number of degrees of freedom in your polynomial, and you cannot fit a straight, I was about to say vertical. No, that's vertical, okay. A straight vertical line, right? Okay, that's relatively benign, all right? But this is something worth mentioning because you may actually make repeated measurements, right, at the same location as a way of trying to understand what is the uncertainty on an individual measurement. Okay, all right. All right, that's what I said, right? We cannot use polynomials for that. Okay, lie number 3. The model that minimizes the chi-squared is best, right? Or a slightly more nuanced statement, the model with the chi-squared per degree of freedom, or reduced chi-squared, that is closest to 1 is the best. Raise your hand if you've heard this statement or something similar. Okay, so we're very close to 100% now. So this is a statement that is somewhat ubiquitous. All right, so let's look at another example. Okay. All right, so all right. So here we have some data, same data we had previously. We have two models. One is a first-order polynomial, also known as a line. The other is a 14th order polynomial. The 14th order polynomial has a much lower reduced chi-squared than the line. Okay. But ask yourself, as you look at this plot, the line is in orange, the residuals for the line are shown on top. The 14th order polynomial is in green, the residuals for that are shown in the bottom. If you had to understand the relationship between x and y, which would you prefer? The answer is not the 14th order polynomial, which nevertheless has the lower chi-squared value and the lower reduced chi-squared value. Okay. So that's a lie. And you've all heard that one because everybody does it. It's a cheat, right? It's a cheat. Lowering the reduced chi-squared doesn't by any means give you something that is best. Okay. Right? We have a question.
In defense of the people who are claiming that, though, I think they usually mean that within the same model, with the same number of parameters, the set of parameters that gives you the best reduced chi-square is a better model than model as in collection of parameters within the same model.
Okay, yes, so there's a subtle point that I'm sweeping under the rug in order to make a point, which is that, okay, so frequently when people talking about things like chi-squared minimization, they're not actually doing things like changing the number of parameters in the model, as I was doing in the example I showed a moment ago. And so it is possibly a bit of a more fair statement to say that minimizing the chi-squared produces the best model. That is totally fair. I agree. I am illustrating a point here by being both bombastic and unfair, as is my right in giving the introductory talk to this session. Okay. So as we discussed, right, if you just look at those two models, right, using chi-square alone will not actually tell you about which of those is better or worse. Okay. And certainly the 14th order polynomial, right, you would never use that particular model to try to estimate the value of y at x equals 50. Okay. All right. All right. So I would say that be a little bit wary if you see things about chi-squared minimization. All right. Again, there are different situations where this is more appropriate than others. All right. I will also say I have papers, if you go dig through the archive or NASA ADS, where I say, hey, I've minimized the chi-squared, so this is the best model. All right. All right. This raises a very important and critical question. How do you actually look at a model and decide that it is in fact the best? This is way beyond the scope of what we're talking about this morning, but we'll touch on this a lot more later this week, in particular Thursday and Friday. Okay. Lie number 3. You cannot fit a model with more free parameters than there are data points. So raise your hand if you've heard this or something very similar to this at some point in the past. Okay. Again, we are close to something like 100% have heard something along these lines. Okay, so let's suppose that you have the following data set. Right? Okay. All right, so this is slightly different than what we had before, but we have some observations with x and y values, right, for every x and y pairs for every observation that has been made. Okay, all right. So if you also suppose that y varies linearly with x, and perhaps we have some theory to guide that intuition, we'll assume that we do in this case, right? But that the data themselves, the observation themselves, are produced via some noisy process, right? You can actually then, assuming again, Gaussian uncertainties for the noise properties, the probability of any individual observation is just itself a Gaussian, where you compare in the exponential the difference between your model and your observation, and then you have some normalizing factors of the uncertainties. Okay? M is the slope of the line, B is the intercept. Sigma sub I is an unknown uncertainty on each of the individual observations. Okay? I'm being a little sloppy in my notation, don't worry about that for now. Okay? So then if you want to understand what is the probability of each of these observations, assuming that they're all drawn independently, an assumption that we will make, then you just have to multiply together all of those individual probabilities, right? Just shown with this capital Pi symbol here. So now we have a model for this data. Okay? The model has 20 parameters. So there's a slope, there's an intercept, and then there is an uncertainty that is unknown that we are going to try to fit for each of these 18 observations. Okay? So 18 different sigma sub i's that we want to know. It's crazy, right? Okay. I mean, there's no way, right? We don't know the uncertainties on any of these things. We can't. We should stop, right? All right. So I'm hiding the particulars here, but let's try to fit this model. And we'll talk in detail about how you might actually fit this model in the future. Okay? It takes a little bit of time. This is certainly not as fast as just running a linear least squares fit. Okay? But it is, in fact, possible to try to figure out what is the slope in the intercept of this line when we have 18 data points and 20 parameters within our model. Okay? Requires a little bit of patience. But we'll get there. Anyone nervous right now? It's very quiet. I can feel the tension. Surely this is not going to work, right? I'm making you wait just so that you can see that actually this isn't possible. All right. And here we go. All right, so let's look at the results of our model. So we have fit for the slope and the intercept and the uncertainties on all of the individual observations. Here I am showing my estimate of the slope and the intercept with the contours there, okay, as well as the correct value. Recall that this is simulated data, so I know the answer in this case. I know exactly what the slope and intercept are. That's what's shown by the blue lines or the square symbol in the lower left-hand panel here. And so even though I just fit a model with more parameters than there are data points, I was actually able to recover the correct slope and intercept of this particular line. Right? A little bit of bias in the fit, but we got the right answer. Okay? Black magic. Yes. We have a question.
Hello?
You're good?
Okay. So like, does this just take a while just because of like how like the analysis done, or would the time vary depending on like how different like the number, like the parameters versus like the number of like data points? It was like further like away. Would it take longer? Would it be like shorter? Does it not matter? Like.
Yeah. So the question is, why did this take so long? Really, I just put a giant pause in the code to build anticipation. That's not actually true. So the method that I used to perform this particular fit, which we will discuss in a great deal of detail over the course of this week, this is why I've obscured at the moment how this was done, is more computationally intensive than something like making a linear least squares fit. And the reason for that is because there are many different parameters, and you have to make some effort to understand what is the correlation between all of those parameters before you can arrive at some final inference. Okay, so it will take a long time. As the number of data points grows, if you also have the number of parameters growing essentially proportionally, you will also then run into extremely long computational times. So, right, the upshot is, for this particular model, right, essentially saying, I have data, but I know what none of the uncertainties are, so I'm going to try to estimate the uncertainty on every single observation, I would essentially never recommend trying this in practice. Okay, this was just for an example to prove a point this morning. Okay? But this will be a very slow thing to actually implement if you were hoping to do so with some real data set, particularly if you had a massive data set like you might have from LSST. Right? This was only 20 only 20 observations. Essentially, this will not scale well if you have a much, much larger data set. Okay. All right. Nevertheless, one second. Nevertheless, this is somewhat amazing, right? So we had no idea what the uncertainties were in this case, and yet we were able to recover the correct slope and the intercept of this line. Okay. All right. So we have a question.
So in this case, it was a line, but in general, if your model is not linear or something, then would this also depend on, let's say, how different the weightage of different parameters are, right? So let's say you have coefficient of some x to the power 4 versus coefficient of x to the 1. So the weightage of different parameters would be different. So in that way, you know what I'm saying?
So I think the question is, I'll try to rephrase, but I think the question is, if your model is very different than the particular model that we considered in this case, would you still be able to implement a fit along these lines? So the short answer is that it will all depend on the specifics, and it will really depend on the quality of the data set that you have. Okay, so going back to the question I raised a moment ago, what is the best model? Here's what's really tricky about that, right? So suppose you have some data. There is literally an infinite number of models that you could consider when trying to understand the relationship between your data. Okay? And so picking best when there is an infinite number of possibilities is, in some respects, an impossibility. Okay? So thinking about what is the appropriate model, and we have an entire lecture on this, to choose given some data that you have later this week, is a challenging question. So answering, can you do this for some other function or some other type of data? The short answer is probably, but the particulars will really matter in that case. Okay? All right. So I hope at this stage I've convinced you that some common tropes regarding least squares fitting do not always apply. All right. I also hope that I've raised a few concerns on your end about what are the best methods. How do you actually go about performing inference or performing forecasting, even for something as simple as two-dimensional data where you'd like to understand the slope and the intercept of a line. Okay. All right. So now I want to spend a bit of time talking about the other major problem for least squares fitting. Okay. Outliers. Right. And we'll do this after the break, actually. All right, welcome back from the break. So before we left, we were talking about least squares fitting and some of the problems associated with least squares fitting, many of which can be understood as the assumptions that are made in order to perform a least squares fit, assumptions that are not often or possibly even ever valid for astronomical data. So today, we're going to continue right now by talking about outliers, right? How do we deal with outliers? All right, so suppose you have the following data set, and that you do have good reason to believe that the data are drawn from a linear relationship. Okay, so here's your data. All right. So these data may seem like they have been drawn from a linear relationship, and you may want to know the slope and intercept of the line, right? But clearly there were outliers. This is not data that just falls on a simple line. So what do you do let's take a minute and discuss this with our partners. Okay. So what would you do? Someone please share. Yes? So we have Carl first.
So you'd want to make sure that it's actually an outlier and not, you said what to do with outliers, but do we know absolutely that they're outliers and not some interesting aspect of the data?
Okay, so there's some question of how do you actually know whether or not something is an outlier? Yes, I think that's an excellent point. Emily, yeah.
So I'm always skeptical of instruments, so I would check the data release notes or check your data observation notes. Where did the data come from? Is there some instrumental thing that could be causing these outliers? Is there an explanation for them?
Okay, so try to see if there's an explanation for what looks a little bit different than what you might otherwise expect via whatever resources you might have. Yeah, I think that's great. Wonderful. Other ideas? Yes, Ahmad.
If I had reason to believe, or I had looked and I knew that these things were outliers, so I was trying to get an estimate of the slope, I would probably do something where I fit a line and then I remove things that are, say, a 5 sigma outlier away from that line and then fit it again.
Okay.
For some number of iterations.
Okay, so maybe try a fit, see what doesn't really match the fit, throw away the stuff that doesn't match the fit, try the fit again, and maybe iterate. Yep. Okay. Other ideas? Yeah, Danny? So it's the black button.
Just wait. You could also try to incorporate outliers into your model, like giving your data points the possibility of either being in the line or an outlier cloud or something.
Okay, so yeah, we just had a description of something that's called a mixture model, which we'll talk about in more detail a lot before the end of this week. But the idea is essentially, can you actually model your outliers in addition to the points that maybe fall on the line? Okay, yeah, all of these are great ideas. I want to talk about sort of a few of the common approaches that you might have to undertake, particularly if you're doing something like a linear least squares fit. Okay, so let's just start and let's just fit a line, right? We saw that one way you can get the slope and intercept is with least squares, so we will apply that. And in particular, we'll do one thing slightly different in this case. So previously, we weren't incorporating weights. The weights essentially are just the inverse of the variance for the individual observations. So it's telling you not just what is the discrepancy between the observation and your model, but it's how large is that discrepancy relative to the uncertainty on that observation. Okay, so we can run this function. All right, and so we can see here that for linear least squares, right, these outliers have a significant effect on the line that we actually fit, right? I think it's very clear that this particular line does not match the data. We wouldn't want to use this for either inference or forecasting. Okay, so we need to figure out something else, and we heard a few ideas about that just a moment ago, right? So can we just throw away the outliers, right? Which is something that was suggested. But this gets back to the point that Carl was making, which is that it's really difficult to actually say what is and what is not an outlier, right? So it seems like there are 4 outliers in this particular case, but there's also a point at about x equal to 23, world's biggest pointer, right? Is this an outlier? I don't know, right? That's a little tough to say. So how do we actually quantitatively decide whether something is or is not an outlier? We could use an iterative procedure, as Ahmad suggested. This is often referred to as k-sigma clipping. So the idea is you pick some k, normally some large number like 5. So if you have 20 data points, you wouldn't expect something that has Gaussian variance to be 5 sigma away from the mean, right? So you can then fit the model to the data. You identify any observations that are greater than k sigma away from the model. You remove those points, and then you fit the model again. And you keep redoing this procedure until there are no outliers remaining. Okay. All right. But there's a major, major problem with this particular approach, which is how do you choose k? So if I have one observation that is 5.0001 sigma away from the line, I will reject that observation. If I have another one that is 4.0001 9999999999999 sigma away from the line, I still keep that point. Are those points really different? Are they really that different? Furthermore, in the initial fit that you perform, the outliers are present, right? And as we saw just a moment ago, that will bias the fit, right? In this particular case, it gave us a slope that is much flatter than we might otherwise think is likely the correct answer. And in biasing the fit in that way, they're actually going to reduce, if you will, the amount to which they are, in fact, outliers. Right? So these are two tricky things if you want to do an iterative procedure like this. Nevertheless, if you have lots and lots of data with a small number of outliers, this can be a procedure that's very useful, right? Particularly in things like pipelines where you know that there's some systematics, you don't want to fully characterize them. You just got to get to an answer quickly. Okay. So ultimately, the challenge, if we want to use something like least squares, is that the outliers, the challenge, if you have outliers and you want to use least squares, is that we have a distance squared loss function. Okay? So I'll skip the derivation for right now, but in least squares, the best model, as we talked about before, comes from minimizing the chi-squared or maximizing the likelihood. These are the same thing. Ultimately, what you're doing is you're trying to minimize the sum that I have shown on the screen here. So we're comparing the model to the y values, the actual observations, taking the square of the difference, dividing that by the uncertainties, and taking the sum. So minimizing this particular function, gives you your least squares result. Okay? But if you have an outlier, the distance, y minus model, is quite large, and then you square that distance, and so your outlier is going to have a very disproportionate effect in terms of the final model that you infer while performing this minimization, right? Okay. So the term that's being minimized in this case is called the loss. So another approach, all right, sorry, and as I said, outliers play a far larger role in your final answer than any observation that is close to the line itself, okay? But in practice, any loss function can be adopted, right? We don't have to use a squared loss function as we were. And so instead of rejecting outliers, we can actually just figure out a way to de-emphasize them by changing the loss function. And this is something that was very famously done by Huber. So the Huber loss function is one way to actually include outliers in a fit, but to de-emphasize them, right? Briefly, the Huber loss is quadratic when you are close to the model that you are trying to infer, but it transitions to a linear loss function, meaning that the distances don't enter into the sum as a square, but just as the distance itself, beyond some critical value c. Right? So to get some sense of what this looks like, I have a plot. All right. Okay. So the squared loss function, or what you typically would be doing with linear least squares, is the most steep function that you can see here in blue. And then these different values c are the critical number of standard deviations, or sigma, you are away from the model. And as you dial down c to lower and lower values, you end up with a linear loss function. So if you are 5 sigma away and you have a squared loss function, that's going to contribute 25 to your sum. Right? Whereas with a Huber loss function with c equal to 3, you're going to get something more like a 5 sigma is only going to contribute like 15 or so to your sum. Okay? So you're de-emphasizing the outliers. So if we apply this Huber loss, okay, we can actually fit the exact same data set, including the outliers. So we're not making any decisions about what is and is not an outlier. Okay? And here's the result in green and the residuals from the Huber loss, the use of the Huber loss in the bottom here. In this case, C has been set to a number I don't remember. I think 3. I think 3. It's in the code that you now have, okay? But we can see by adopting this Huber loss, we get something that looks far more reasonable, right? If we were going to try to either infer the relationship between these data or forecast what's going on, you would much, much rather use the results from the Huber loss than from least squared minimization. Right. Okay. But there should still be something that's nagging you. We have a question. Yes. Yes.
Yeah, here. So why is it different to, what is it better to choose the C in the Huber loss than the K in the clipping?
I paid Rocio to say that because you should still be nagging yourself about how you choose this value C, right? Which actually will critically inform the final answer that you get in adopting a Huber loss function. And unfortunately, there is no mathematical guidance for what you should pick as C, right? So to say I pick C at 3 instead of C of 5, right? There's no obvious reason or mathematical motivation for making a choice along those lines, right? So there is somewhat of an arbitrary decision that's been made if you want to use a Huber loss function, okay? So this should leave all of you thinking, there has to be a better way! And indeed, there is a better way, all right? And we're going to talk about this a lot. If you think this talk is the last time you will see data from a linear relationship with outliers, you got something coming. All right. Okay, so quickly, just really quickly in closing, before we move on to the problems, I want to briefly touch on probability theory. Okay. All right. So suppose you have some event, and we will call this event A. All right. We will define the probability of this event occurring as P of A. Right. So P is for probability. A is that that event will occur. Right. Now suppose that we want to know the probability that both event A and event B occur, right? Which has this symbol P union A and B, all right? So at first glance, it seems like the probability of one event and another event should just be the probability of each of those events multiplied together. And this is true in one very special circumstance, and that is that A and B are independent. But if they are not independent, then this is not true. And we can demonstrate this very quickly with a coin, right? So imagine you just have a single coin and you want to flip it. Event A is that that coin lands with heads. Event B is that that coin lands with tails. So if I flip a coin once, the probability of A times the probability of B is is a half and a half, right? I have a 50% chance of heads or tails. So that gives us 1/4. However, if I flip a coin once, the probability that it lands in both heads and tails, right, A and B are true, is very clearly 0. This is not possible. Okay. All right. So what that means is that we actually, if we want to consider multiple events that are related, we have to look at conditional probabilities. So this is the probability of A and B is equal to the probability of A given that B is true. So we're going to look at if B is true or not before we consider whether or not A is true, multiplied by the probability of B. If we return to our coin flip example, all right, so then if we flip the coin and it lands on tails, all right, then the probability of A is 0, and we get that the probability of A and B is 0. So this statement, the probability of A and B, is equal to the probability of A given B multiplied by the probability of B. All right. So the probability of A and B must also be equal to the probability of B and A. Right. So that leads us to the following. Right. So the probability of A given B multiplied by the probability of B equals the probability of B given A multiplied by the probability of A. We can slightly rearrange those terms, and the probability of A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. This is just probability. This may look a bit familiar to some of you, okay? But this is just probability, and it is true. I want to emphasize this. Okay? This equation here is Bayes' law. Bayes' law is 100% true. We just derived it. Bayes' law is true. Nevertheless, at times, you may encounter arguments or opinions that are, quote, anti-Bayes. And I just want to emphasize that these sentiments, right, anyone that maybe says, I don't like Bayes, or I don't want to use Bayes, or anything along those lines, right, all of those have to deal with the interpretation of Bayes' law. none of these things have to deal with whether or not Bayes' law itself is true. We just derived it. We are going to cover in great detail over the course of the remainder of this week, and this afternoon especially, the interpretation of Bayes' law. Right? So I'm not going to go into any further detail right now. All right, so problem 6, this is the problem you'll be working on, forecasting. All right, so you have a cell, you can execute it, you'll get some data, x, y, and y uncertainty. And so using this data, all right, from problem 4, I want you to create a forecast for the value of y at x equals 6. Right? I want you to generate as many forecasts as you can using different methods. And to be clear, a least squares fit with a first-order polynomial, a second-order polynomial, a third-order polynomial, and a fourth-order polynomial is a single method that has been applied 4 times. All right? So a for loop where you've done that over 1,000 values is not 1,000 different methods. All right? I also want to note that these methods do not need to pass the, quote, referee test. All right? So I want you to essentially think of any way that you can that you might be able to forecast the value of y at x equals 50 given the data. Okay? One super important critical boundary condition. It is required, I'm going to say that again, it is required that you talk with and work with your partner on this exercise. All right? This is not a contest. This is not a race. If you want to try something that your partner is not familiar with, so for instance, we had a relatively complicated suggestion of building a mixture model. Right? We will all learn about that over the course of the week, but if your partner doesn't know what that is right now, then you have to stop and take the time to explain that to your partner to the degree that they fully understand before you implement the mixture model. Okay? Or any other method you want to use for forecasting. Right? So please do a git pull. You should be talking this entire time. All right? This is a relatively open-ended problem that is intentional. We expect you to be working with your partners. I will be walking around to answer any questions. Okay? And we'll share some answers shortly before the lunch break. Before we begin, let me ask, any questions on the lecture? What's the referee test? So the question was, what is the referee test? And what I mean there is that something that if you put it in a paper, a referee would accept it. Okay? So you can forecast with techniques that a referee would reject. I am fine with that for the purposes of this particular problem. Okay, so we're all just going to chat a bit now about different ways that we might go about forecasting the value of y at x equals 50 given the data set in hand. Okay, so I'm curious, right, first and foremost, anyone come up with anything that would not pass the referee test? Yes, we have a few. So just turn on your mic. Someone? Anyone? Joey, you raised your hand. You want to pop your mic on and tell us what you did?
I just stole a Huber regressor object from scikit-learn.
Okay.
I don't know.
All right. So the suggestion was Huber loss function.
Yeah.
I actually think that a referee very well might accept that. So I would say that that will pass the referee test. Anyone else? Something that won't pass the referee test? Husni, can you turn on your mic, please?
Oh, it's green.
I made a decision tree regressor.
You made a decision tree. Okay, again, we have statistical underpinnings for what is happening here, mathematical functions. I think that there are referees that would accept that. Okay, we'll come back to that in a second. Okay, Yuping?
Well, I took the Huber loss function, and I flipped the x and y in there, and I tried to minimize the residuals and x.
Okay, so again, we're using mathematics and the Huber loss function. There may be referees that would accept that. Bridget?
So basically, there's a point at roughly x is 40, and another point at roughly x is 60.
Uh-huh.
So I took the average of the two.
Okay. Yes. What referee is going to accept that? None, right? Okay. Okay, let's see. So my first non-referee proof solution, all right, is I created a small function. I knew we would be creating a lot of forecasting here, so let's execute that. My first non-referee proof solution, just guess! The data kind of go like that. 50's right there, red star, 57. Okay, this is definitely not referee proof. Nevertheless, this is not terrible, right? 57 is not that far off from the correct answer. Okay. All right. Linear interpolation we just heard about between those 2 points. I did that as well. Okay. So here we can let's see. There we go. So basically with NumPy, you can interpolate between each of the individual data points. The bright red star here is the prediction at 50. Okay. The faint red line, which may be a little bit hard to see, is the prediction at any other point. Okay. At 50, for this particular data set, it's not too terrible. You make predictions elsewhere, you're definitely not passing the referee test. Right? Okay, so let's talk about some things that maybe would pass the referee test. So we heard Huber loss. A few people did that or some version of that. Anything else? You all did Huber loss functions? Did anyone use least squares? Okay, I see a lot of people nodding. Okay, yes, so least squares, that would work. That's fine. Yes. Any other methods? Yeah, we'll do Rocio, and then Ian will do you next. Yeah.
The 3 sigma clipping.
Okay, so we had an implementation of sigma clipping. Okay. Roughly, what did you get as the value for y in that case?
57.7.
That's what I guess with my eye. Same thing. All right. Ian?
Yeah, so I just basically, got scikit-learn runner and did any kind of regression that they had in there. And so that included some extremely bad ones.
Okay.
Because I just used default hyperparameters for everything.
Okay.
So for instance, Gaussian process came out as an erratic mess, which is
okay.
amazing.
All right. So Ian essentially used several different methods within scikit-learn. So this is a library in Python where you can implement machine learning models, for those of you that aren't familiar. And some of those worked and some didn't. Yeah. Anything else? Imad?
I did just try to write a quick k-sigma outlier rejection thing. I got 54.5.
Okay. Yeah. Anything else? Yeah, Kevin?
So I tried so if you assume the data is smooth, you can do a moving median filtering of outliers. The problem is that if you do use a moving window of 3, then the last outlier ends up not being detected because there's not enough room for it to calculate a moving median.
Okay. Yeah. So the idea here basically is just take a chunk of points, in this case 3, right? And then just take the median at every position of the 3 closest points, and then you'll get some kind of relatively robust metric for what the value of y should be at any value of x. But at the boundaries, that doesn't work particularly well. Yeah. Okay. Anything else? Nancy, did you? No. Okay. Sorry. Okay. Another one that you might see often, and I forget exactly what order I did everything here. Is this one next? Yes. So spline fitting is maybe something you've heard of. Okay. So here is the results from spline fitting, right? This gets pretty crazy at the boundaries. This is one reason why I would typically not recommend using spline fitting as a way of doing forecasting. Okay. And that says that's my last slide, but I have other solutions. Oh, I didn't make them new slides. Okay, so weighted least squares, right? That looks like this. Huber loss function, that looks like this. For those of you that are curious, not that they all look this way, but I did implement one machine learning solution. So this is the use of a random forest regressor. Okay, and so the red line there shows the predictions at any given point. Doesn't look so great, right? Okay, but there are ways that we could probably tune that to make this work a bit better than what you see here. All right. So that brings us to the end of this morning's lecture. I hope you had a bit of fun. I hope you felt like you got to be a little bit creative in figuring out how you would forecast the value of y at x equals 50. I will ask one last time, are there any questions on lecture or the problem that we just worked on? Yes, Ian.
I was just wondering if, like, I was trying to remember off the top of my head, what are typical ways of using the uncertainties to do weighting?
So the question is, what are the typical ways that you might use the uncertainties to weight the observations? So the standard is under the assumption that the uncertainties are Gaussian and that you correctly know the variance, the typical weight that would then be applied to any single observation is the inverse of the variance. And if you go through and you sort of do the integrals with the Gaussians, you see that this is essentially an optimal statistic, particularly if you have a squared loss function, which again, a lot of all the different things that we were considering today are sort of slight modifications on least squares minimization. That being said, you can come up with other weights, right? And it may or may not be some ad hoc approach. There's also ways that you can, if you're, say, building a full model, and we'll talk about this in more detail over the course of this week, where you might say, I suspect that there are systematics in my data, but I have no knowledge or idea what those systematics are. And you can make general modifications to things like your weights, assuming that they're systematics, but you don't know what those systematics are, and still be able to make reasonable inference. Okay, and that's a relatively complex problem, particularly when compared to something like linear least squares. But we will touch on that several times, right? Data that looks like this, you're going to be looking at it all week long. Okay, looks like a line, but there's some outliers. What do you do, right? That question will come up again and again and again.